When we talk about measurement in science, we usually think of numbers. For example, we might say the length of a table is 120.0 centimeters, or the mass of an object is 2.35 kilograms. But behind every measurement, there is something we must never forget: uncertainty. No measurement can ever be perfectly exact. There are several reasons for this. First, limitations of instruments. Every measuring device, from a simple ruler to a sophisticated digital balance, has a smallest division it can read. For example, if a ruler is marked in millimeters, we cannot claim to measure beyond that precision. Second, human error. When we read scales with our eyes, we might not align them perfectly. For example, parallax error occurs if we look at the scale from an angle. Third, environmental factors. Temperature, pressure, and even vibrations in the environment can slightly affect readings. And fourth, variation in repeated measurements. Even if we measure the same thing multiple times, small differences will appear. It's important to distinguish between uncertainty and error. Error means a mistake or a deviation from the true value. Uncertainty is not a mistake. It is an honest statement of the range within which the true value is expected to lie. For example, if you measure the length of a pencil as 14.3 plus 0.1 centimeters, you are saying, I am confident the real length is somewhere between 14.2 and 14.4. Uncertainty can be expressed in two main ways. Absolute uncertainty, the actual size of the uncertainty in the unit of measurement. Example, a mass measured as 250 grams plus 2 grams has an absolute uncertainty of 2 grams. Relative uncertainty, the ratio of the uncertainty to the measured value, often expressed as a percentage. Example, for 250 grams plus 2 grams, the relative uncertainty is 2 divided by 250 times 100%, which is 0.8%. Relative uncertainty tells us how significant the uncertainty is compared to the value itself. In real experiments, we often combine different measurements. For example, calculating speed requires both distance and time. So how do we handle uncertainties when values are added, subtracted, multiplied, or divided? In addition or subtraction, we add the absolute uncertainties. Example, 12.5 plus 0.2 centimeters plus 7.3 plus 0.1 centimeters equals 19.8 plus 0.3 centimeters. In multiplication or division, we add the percentage uncertainties. Example, 4.0 plus 0.1 meters multiplied by 2.0 plus 0.2 meters equals 8.0 square meters, with a relative uncertainty of 11%. This method ensures that uncertainties are carried through correctly, showing the final reliability of results. Scientists aim to make uncertainties as small as possible. Some ways to reduce them are using instruments with higher precision, taking repeated measurements and calculating the average, controlling environmental conditions, and using digital devices to minimize human reading errors. Uncertainty is not a flaw. It is an essential part of science. It makes our measurements honest and trustworthy. Without uncertainty, measurements can be misleading. For example, a claim that a length is exactly 14.300000 centimeters may sound precise, but if the ruler only measures to the nearest millimeter, such precision is false. Science values truthfulness, and uncertainty is a way of being truthful about what we know. Every measurement carries uncertainty. Uncertainty comes from instrument limits, human error, the environment, and natural variation. It can be expressed as absolute or relative. There are rules for combining uncertainties in calculations. And most importantly, stating uncertainty makes science honest, accurate, and transparent. In short, uncertainty is not a weakness of measurement. It is the very thing that makes measurement scientific.